So in this lesson, we want to start putting together all of the things that we have done in previous units about finding information about curves, combine them with our rules for finding the derivatives of exponential and logarithmic functions and what we know about exponential and logarithmic functions, and be able to sketch the graphs of exponential and logarithmic functions. So we're going to end up talking about we're going to follow the usual steps that we've done all along here. We're going to have a couple of functions. We are going to first find the first and second derivative of these functions, and then we're going to investigate the domain, the asymptotes or the end behavior, the intercepts, the turning points or the local maxima and minima, the intervals of increase or decrease, points of inflection, intervals of concavity, and that'll give us enough information that we can go ahead and sketch our graph. So the first function that we want to sketch the graph of is the following, x squared times e to the x. So let's start by finding our first and our second derivative. This function here is actually two functions multiplied together, so we're going to have to use the product rule. So our derivative is going to be derivative of the first function, which is x squared, so 2x e to the x, plus our original first function, x squared, times the derivative of e to the x, which is just e to the x. Now likely I'm going to want to factor this expression here, so let's see what is common to these two terms. An x is common, e to the x is common, and that leaves me with a 2 plus x. So there's my first derivative. How about my second derivative here? Well, the second derivative is a little bit trickier. Okay, I've got a bunch of functions here. I can think of this as being two functions multiplied together. This is my first function, and this is my second function, u and v. But u is itself two functions that are multiplied together. And in fact, it's the original function that we had before. So I need to use the product rule when I find the derivative of u. So maybe I'll just do that over on the side here. U primed is going to be, let's see, the derivative is going to be, oh sorry, it's not the original function, but the derivative is going to be derivative of the first one, x, which is going to be e to the x, plus x times the derivative of that second function, e to the x, so x e to the x. So when I put this together, doing my product rule, I'm going to have e to the x plus x e to the x, that's u primed, times v plus my original u function, so x e to the x, times v primed. Well, v primed is just 1. So what do we have here? Well, we've got a bit of a mess. Let's expand it and collect our like terms. So I'm going to have 2e to the x plus 2x e to the x plus x e to the x plus x squared e to the x, so that's expanding that binomial, plus x e to the x. Now, what terms can I collect together? Well, let's see. I've got 2e to the x, doesn't match up with anything. I've got three terms that are x e to the x, so 2x, let's just underline those, 2x e to the x, 3x e to the x, it's like 4x e to the x, so plus 4x e to the x, plus x squared e to the x. Now I want to factor this expression, so I can factor out the e to the x, and I'm left with, rearranging it, x squared plus 4x plus 2. Does that trinomial factor? No, it doesn't, so I'm just going to leave my, second derivative like this. So there, I've got my first derivative, and I've got my second derivative. So we're going to need them as we go through the rest of our analysis here. So let's just jump onto a new page here, and let's think about the domain of this function. So remember, our function is y equals x squared e to the x. There are no restrictions on either x squared or e to the x, so our domain here is just x is an element of the real numbers. Next up, let's consider our asymptotes. Okay. Vertical asymptotes usually occur where places where the function is undefined. So if our function is defined everywhere, we have no vertical asymptotes. Horizontal asymptotes. Well, we've got this exponential function e to the x, and we know that e to the x kind of has a horizontal asymptote. If we sort of remember what the graph looks like of e to the x, something like this. Let's just label this e to the x. So it tends to 0 as x goes to negative infinity, but it goes off to positive infinity as x goes to positive infinity. So to figure out what our function does, let's consider the end behavior here. So I'll just cross out horizontal asymptote, and I'll say end behavior. And to get a handle on the end behavior, let's evaluate the limit as x goes to positive infinity of our function, x squared e to the x. And let's just think about what each of these terms are going to be doing. As x goes to positive infinity, x squared is going to go to positive infinity. And as x goes to positive infinity, e to the x is going to positive infinity. So we end up with something that is like positive infinity times positive infinity. That's going to go off to positive infinity. What about the other direction? X tends to negative infinity. Again, let's consider what x squared and e to the x are going to be doing. X squared is going to be going off to positive infinity again, but e to the x is going to be tending towards 0. So 0 times positive infinity, I think this is going to tend towards 0. So we've got the same end behavior here as we had in our original, in a straight exponential function. Let's see, our intercepts are next. If we want to find our x-intercept, we want to figure out where y is equal to 0. So we can set our function equal to 0. That's x squared e to the x. And we've got two terms here, x squared times e to the x. So we can take each of these and set them equal to 0. X squared equals to 0 gives us x equals 0. E to the x equals 0 has no solution, because that e to the x function is never going to reach x equals 0. Our y-intercept, we want to sub in x equals 0. So what happens when we sub in x equals 0 to this function here? We get y equals 0 squared e to the 0, which is just 0 times 1, which equals 0. So we have one intercept that is both our x-intercept and our y-intercept, and that is 0, 0. So after our intercepts, we want to take a look at our intervals of increase and decrease and any local maxima or minima. So first we want to find our critical numbers, which are points where our first derivative is either 0 or it doesn't exist. So let's try f primed at x equals 0. Our first derivative was x, not x squared, but just x, e to the x, 2 plus x. Let's set that equal to 0. This is going to, because this is already in factored form, we can just take each of our terms, our factors, set them equal to 0. So we get x equals 0. We get e to the x equals 0, which we know has no solution. And 2 plus x equals 0, which is going to give us x equals negative 2. Critical numbers also occur where our derivative does not exist. but there are no points where our derivative doesn't exist. So we've got two critical numbers, x equals 0 and x equals 2. So let's use them to set up our interval table. We're going to have intervals from negative infinity to negative 2, from negative 2 to 0, from 0 to positive infinity. And again, we're checking the sign of each term in that first derivative. So x, e to the x, 2 plus x. And we're trying to figure out overall what is the sign of our first derivative and what does this tell us about our function. Well, x is going to be negative, negative, and then positive. E to the x is always going to be positive. 2 plus x is going to be negative, and then positive, and then positive. So our first derivative is positive, negative, and positive. So our function is increasing, decreasing, and then increasing again. So it looks like we have a local maximum and a local minimum. We're going to have a local maximum at x equals 2. Okay? And we know this is a local maximum because the other possibility is it could be a vertical asymptote, but we know our function is defined everywhere. So this is going to be a local maximum. And we should figure out what the y value is here. Punching this into our calculator, we get 0.54. And then we're going to have a local minimum here at x equals 0, which we have already found is 0, 0. Next up, let's investigate the concavity of this curve. And to do this, we are going to need to use our second derivative. We're going to find our critical numbers where our second derivative is equal to 0 and where our second derivative does not exist. Our second derivative is e to the x times this quadratic, x squared plus 4x plus 2. So possible solutions are e to the x equals 0. We know that this has no solution. Or where x squared plus 4x plus 2 equals 0. This is not going to factor, so we're going to have to use the quadratic formula to solve this. So quadratic formula gives us solutions of x equals negative 3.41 and x equals negative 0.59. So 2 points of inflection. Are there any points where our second derivative does not exist? No, there are not. So let's set up our interval table here. We are going to go from negative infinity to negative 3.41, from negative 3.41 to negative 0.59, and then from negative 0.59 all the way up to positive infinity. And we're checking the sign of each of these terms in our second derivative. So e to the x and x squared plus 4x plus 2. And we want to figure out what is the sign of our second derivative. What does that tell us about our function? E to the x is always positive. We know that. Now for this term, x squared plus 4x plus 2, I think you just want to take a test value from each of these intervals, sub it in on your calculator, and work out what it is. So something like negative 10 from this interval, maybe negative 2 from this interval, and maybe, oh, you could even put in 0 for this interval over here. So we're going to get, working backwards, that's going to be positive. This one is going to be negative, and this one is going to be positive. So our second derivative is positive, negative, positive. So our curve is concave up, concave down, and then concave up. So we're going to have 2 points of inflection. The first one is going to occur at negative 3.41. The second one is going to occur at negative 0.59 something. Okay? I don't know exactly what those y values are, but it turns out I already have enough information here to sketch the graph of my function. So let's go ahead and try to sketch this graph. First thing I'm going to do is I'm going to put on my asymptotes, or my end behavior. Let's see, so my end behavior was that my function has to go off to positive infinity up here, or as x goes to positive infinity, and it has to end up tending towards 0 over at as x tends to negative infinity. My intercepts, I had one intercept here at 0, 0. My local maximum, I had a local maximum at negative 2, 0.54. So I'm just going to scale up my x-axis a little bit here. Let's just ignore this scale that we have here, and here, and here. And we'll say that this is 2, and this is about 0.5 right there. So this is our point, negative 2, 0.54. And then I have points of inflection at approximately negative 3.4. So if that's 2, negative 3, so somewhere over here, I'm going to have a point of inflection. And another one at negative 0.59, which is going to be another point of inflection somewhere along here. Okay. So these points of inflection, I didn't calculate the exact values, but I can see kind of that they're going to be in here, and they're going to be in here like this. So now I will just want to draw a smooth curve that matches up with my end behavior, and before I do that, I should make use of my intervals of increase and decrease. I know that my function is going to be increasing all the way up to this local maximum. Then it is going to be decreasing to here, and then it's going to be increasing after here. For my concavity, I know that it is going to be concave up till this point of inflection. Then it's going to be concave down over to my next point of inflection, and then it's going to be concave up for the rest of the time. So my curve should be increasing, go through this point of inflection, change over to decreasing, go through this point of inflection, go through this local minimum here, and then be increasing again. So there's the sketch of my function. Local maximum right there.